All right, relatively fast lesson of the day, going back over limits. Last time, right before our midterm, I think, I gave you guys a limit cheat sheet that I've just reposted to the WeChat. This goes over everything you need to know for the final. I'm going to make a couple marks of things that you won't need to know for the final as we go through. So you will have a section on continuity. So you'll have to label things as continuous, removable, or non-removable. I'm not going to be looking for subcategories that are tested on the AP exam of non-removable discontinuities, so if you can just label all of these as non-removable. A function is continuous as long as the limit from the left is equal to the limit from the right, so that means you have a general limit, and when you plug it in, you get the same point. So here, as I approach x equals -2 from the left and the right, both from the left and the right, I'm getting really close to y equals 4, and then if I actually plug in -2, I get y equals 4. Versus here for removable discontinuity, your limit from the left is the same as the right, but when you plug it in, you get something different. So that would be something like this. As I get really close to x equals -4, I'm getting really close to y equals 2. But if I try to plug in the point, this is a white dot, which means it does not exist. Since d&e is not the same as 2, our general limit is not the same as what happens when I plug in the point. So this is a removable discontinuity. Okay, another way this could happen is something like this. So here we've got y equals 5. My limit from the left and from the right are both approaching y equals 5, but if we actually plug in x equals 6, my y value becomes 2. Another way of thinking about this is that a removable discontinuity is a discontinuity that could be fixed by moving one point. So I could move this point here, and that would fix the discontinuity. I could put a point here, and that would fix the discontinuity by just changing one point. Non-removable discontinuities are everything else. So that's whenever you don't have a general limit, your limit from the left is not the same as the right, or any of your one-sided limits approaches infinity. So a couple examples. Here I've got a vertical asymptote at x equals -1. From the left, I'm approaching negative infinity. From the right, I'm approaching positive infinity as I get closer and closer to x equals -1. Because some of my one-sided limits are approaching infinity or negative infinity, this is a non-removable discontinuity. Also, because my limits are different, would be a second reason why this is a non-removable discontinuity. Okay, more examples. My limit from the left is not the same as my limit from the right. Limit from the left is not the same as the limit from the right. So these are non-removable discontinuities. Limit from the left does not exist, and limit from the right does exist. Those are not the same. So this is a non-removable discontinuity as well. Okay, any questions on continuity? Okay.
So non-removable discontinuity when it's just, how to say that, when it's just a blank space and nothing more?
It's whenever your limit from the left is not the same as your limit from the right. So that could be because there's a blank space. It could be because you're going to infinity or negative infinity. It could be because your limits are different but exist. So all three of these cases are all part of non-removable discontinuities. Okay. Differentiability, this part might be new. In order to be differentiable, we must be continuous, which means we have a general limit and it equals what happens when I plug in the point. But also to be differentiable, the limit of our slopes have to be the same, which means our curve would have to be smooth. So all of my points from here to here are differentiable. And from here to here are differentiable, but this point up top at the cusp is not. I'll show you why. So although this is continuous, my limit from the left is the same as my limit from the right, and when I plug it in, that point does exist. If I look at the slopes, my limit from the left would give me a positive slope here. If I get really close to this point on the left-hand side, my slope is positive because our function's still going up. But on the right-hand side, my function's negative, is going down. Because my limit from the left is not approaching the same slope as my limit from the right, this is not differentiable. Okay, so we are continuous but not differentiable at this point, at the cusp. Any questions on differentiability? Okay, let me draw a couple more examples. So here I've got a sine function. I want to know, is it differentiable? So I'm going to start with Abby. First, is the sine function continuous? Yes. How do you know that the sine function is continuous? Okay, so to be continuous, our limit from the left and the right must equal what happened when we plug it in. Another way of saying this is you should be able to draw your function without picking up the pencil if you are continuous. So in this case, we can do that with our sine function. So we are continuous. Andrew, is the sine function differentiable? Okay, yes. In order to be differentiable, there must be a general limit, which means your limit from the left and the right of your derivative must be the same. So in this case, if you pick any point on this sine function, our limit from the left and the right are approaching the same value. In this case, our limit from the left and the right are both approaching 0 as I get closer and closer to x equals pi over 2. Okay, let's try another. This is y equals 1 over x. As x approaches 0 from the left, I'll have a really small negative number. If I'm dividing by a really small negative number for x, then I'm going to get a larger and larger negative number, so it'll look like this. Same thing if I take the limit from the right, the limit as x approaches 0 from the right of 1 over x is 1 over a super small positive number. If I divide by a super small positive number, I'll get a really large negative, or really large positive number. So this will be something that looks like this. Okay. So first, Eric, is this function continuous? Okay, no, this function is not continuous. At what point is this function not continuous? Where it reaches to infinity. Okay, so I could say at x equals 0. What type of discontinuity do I have? Removable or non-removable? Non-removable, perfect. Okay, Kyle, is this function differentiable? Okay, let me go back. Differentiable. So in order to be differentiable, we must be continuous. So continuous. And our slope from the left must approach the slope from the right. Okay, so going back to our function. It's not differentiable. Okay, why is this not differentiable? Two reasons. Okay, my slope is pointing in two different directions. In this one, the slope is really negative, and in this one, the slope is really positive as we approach 0. So I could say it's not differentiable for two reasons. First, the limit as x approaches 0 from the left of our derivative is not the same as the limit as x approaches 0 from the right of our derivative. And then one more reason. Okay, in order to be differentiable, we have to be continuous and our slopes have to be the same. So, what's the other reason why this cannot be differentiable? It's not continuous. So, we're not differentiable on two counts. Okay. Try a couple more. Okay, so I'm going to say all of the points that are showing are either at y equals 1 or y equals 2. Starting with Nile. At x equals a, I want you to tell me the limit from the left. The limit from the right, the general limit, if it exists, and then what is the actual point. Okay, so Niall's chatting with me. Limit from the left. Okay, I think you're giving me the limit of the slope is... Okay, my limit from the left of x equals a is what y value am I getting closer and closer to as I approach x equals a? Two. Okay, what's my limit from the right? Also 2. What's my general limit? The general limit does exist. As long as your limit from the left and the right are the same, then that will be my general limit. So if the limit from the left is 2, limit from the right is 2, then the limit in general should also be 2. And then if I try to plug it in right now, this is a little bit hard to see, especially with the cursor there. But my function is continuous, so that point does exist. So the y value is also 2. Okay, so everything is 2. Over to Nikita. Nikita, at x equals a, is this function differentiable or not differentiable?
Differentiable.
Okay, this function is not differentiable actually. Can you tell me why?
What do you mean by differentiable?
Differentiable means you can derive it. So why can I not derive this function at x equals a?
Oh, because the slope changes.
The slope is different. Perfect. My slope on the left side is approaching a different value than a slope on the right side. So it's not possible to derive this function at x equals a. Okay, what about x equals b? Is that differentiable or not differentiable?
Just a second. It is different. Oh wait. Just a second. I think it is differentiable.
Okay, this one's not differentiable, but for a different reason.
Yeah, because it's empty.
Because it's empty. Perfect. In order to be differentiable, we have to be continuous, and the limits of our slope have to approach the same value. Okay, what about x equals c? Is x equals c differentiable?
No.
No.
I don't think any of them are.
Don't think any of them are. Okay. You're right. None of the ones that I'm showing right now are differentiable. So x equals a is not differentiable because my slopes are different. B is not differentiable because I'm not continuous. C, D, E, F, and G are all not continuous. So these are all not differentiable. Okay, awesome. Check and see if I have anyone else on Skype really quick. Nope. Okay, so back to the top of the order with Abby. At x equals c, what is my limit from the left? Okay, it is 1. What's my limit from the right? 2, perfect. So what's the general limit then? Perfect. So general limit does not exist because I'm going to different points from the left and the right. And last part, what happens if I try to plug C in? Nothing, because we don't have any filled dots. Perfect. Okay, over to Andrew. Andrew, what's the limit from the left at x equals d? Two. What's the limit from the right? Does not exist. General limit does not exist. And if I try to plug in d, does not exist. Okay, any questions on continuity? Oh, let me do one more at f. So, Eric, at f, what's my limit from the left? Okay, what's my limit from the right? So what's my general limit? Infinity. Okay, and if I try to plug in f, what do I get? Does not exist. Awesome. I believe this might be different on your Korean entrance exam. It depends on where you go. For the Korean entrance exam, I believe they would say your general limit does not exist because there's no one point that you're approaching. On your AP exam, though, they'll want you to say that your general limit is positive infinity, which is a little bit more specific. Means both sides are increasing. However, your y value does not exist. You can't write positive infinity even though both sides are increasing because we don't know they're increasing at the same rate. If they're not increasing at the same rate, one could be at 3, one could be at 2. And there'll always be a different value, so there's no one set value for y. It's very unlikely. Okay, that's continuity. I've got several other types of limit solving problems that are on this sheet. So different ways to solve more difficult limits just on your cheat sheet. L'Hospital's rule does not show up on your exam, but if you know how to use it, you can shortcut. So I'm going to go through that really quick. I did not teach this the first time we went through limits because you have to know how to derive in order to use it. L'Hospital's rule says, if you can split up your fraction into a top part and a bottom part, and you end up getting a limit of I'll do this. Limit as x approaches c of x over g of x. So you end up getting a limit of 0 over 0 or plus or minus infinity over infinity. Then your limit as x approaches c of that function is the same thing as the limit of f prime x over g prime x. Be really careful. This is not quotient rule. We're deriving the numerator and denominator separately. I'm not deriving the whole function. I'm deriving the top and bottom separate. Okay, so as an example, let's say I wanted to derive this. Find the limit as x approaches 0 of the sine of x over x. Next on the order is Kyle. Kyle, what's the sign at 0 if I try to plug this in? Zero. And if I plug it in for x, I also get 0. So I have 0 over 0. So that tells me we can use L'Hospital's rule. For L'Hospital's rule to work, that means this limit should be equal to the limit as x approaches 0 of the derivative of the top divided by the derivative of the bottom, What's the derivative of sine? Cosine. And what's the derivative of x? Not 0? 1. Okay. So now if I plug in 0, what is the cosine at 0? 1. So now I've got 1 divided by 1, or 1. Okay, so the limit as x approaches 0 of sine x over x is 1. Therefore, the limit as x approaches 0 of the sine of x over x is equal to 1. Okay, that's a hospital's rule. Sometimes it can be a shortcut for what would otherwise be a really long problem. I'll see if I can find another example that we can use from the from these other questions really quick. Okay, so this one, for instance, normally the way I would solve this is using our shortcut rules for limits, approaching infinity or negative infinity. So for this one, that would mean something like this. I'm going to look at which side has my largest power. Right now I've got x root 3 plus something else on top. And I've got 4x on bottom. Because my largest powers are the same, I'll end up going to the fraction of my coefficients, which is root 3 over 4. If you didn't like that, you could try El Hospital's rule instead. Right now, if I plug in infinity, I'll get infinity over infinity. So what I could do is derive the top. If I derive the square root of 3 times the square root of x squared, that's root 3 times x, I would get root 3. If I derive 4x, I would get 4. So derivative of the top divided by derivative of the bottom is root 3 over 4 with El Hospital's rule. Okay, any questions on the new rule? And you don't have to know it for your final exam, but it can save you time if you want to use it. If you keep going with me for AP Calculus, you will need to know it. And I'll give you a couple problems that you can only solve using El Hospital's rule next year. But for now, it's just a shortcut. Okay. You guys don't need to know squeeze theorem for your quiz. I don't think we covered that in quarter 1. I could be wrong, but I don't have any squeeze theorem problems in the final exam. For limits approaching infinity, if it's a polynomial and you've got your largest power on top, then you'll approach positive or negative infinity depending on the sign. So in this case, if I plug in infinity, I've got my largest power on top. And when I plug in infinity, both sides are positive. So that means my answer will be positive infinity. My largest power is on bottom. Here I've got x to the 7th power. I'm going to approach 0. And if my powers are the same, I'll approach the fraction of the coefficients. So in this case, 3 over 2. If you don't have polynomials, then you can follow this order guide to see what grows faster. So if your fastest function growth is on top, then you'll approach positive or negative infinity. If your fastest function growth is on bottom, you'll approach 0. And if your fastest function growth is the same speed, then you'll approach the fraction of the coefficients. Factorials grow faster than exponentials, grow faster than polynomials, grow faster than logarithms, grow faster than sine or cosine, grow faster than constants, which don't really grow at all. Okay, so here's some examples with those. I've got a factorial over a logarithm. Factorials grow faster than logarithms, so my power is biggest on top. And when I plug in infinity, that's a positive over a positive number, so this approaches infinity. Here, if I plug in infinity, exponential functions grow faster than polynomials. So because my fastest growth rate is on bottom, I will approach 0. And then here, if I use properties of logarithms to pull this apart, so with power property of logarithm, I can move this power down. I'll get 7 ln x over 5 ln x. The 3 and the 4 are constants, so my fastest growth rate are the logarithms, which are growing at the same rate, ln x, so I'll approach the fraction of my coefficients, which is 7/5. Any questions on any of these three? Okay. I have attached on WeChat 2 previous quizzes that we took, but with step-by-step worked out solutions. So if I let this load really quick to show you. Still loading. Come on, you can do it. There we go. Okay, so it may take a second to load. It'll be even longer if you try to load in your phone, unfortunately. But once it loads, you should see all of the worked out solutions step by step, and how I would grade you for that particular problem. So for instance, for this first one, I'm taking my limit as x approaches 3 from the left of 2 times the absolute value of x minus 3 over x minus 3. Really, because these two x minus 3's are the same, I know that my answer is going to be 2. I'm just worried about my sign. If I plug in 3 minus a little bit, that's like 2.9999999. And 2.99999 minus 3 is going to be a really small negative number. Under the absolute value, that'll become a positive number on top, but will remain a negative number on bottom. So this is 2 times a positive divided by a negative gives me negative 2. Okay, so I'm going to break here because several of you are really good at limits already. I don't want to waste too much time. But if you do want more practice with limits, I've given you lots of example problems to try with all the answers. And then we've got limits final exam practice homework is the homework for today, which is 10 questions on limits in the same format. Okay. If anyone has questions on anything, feel free to stick around. And if not, you guys are free to go. Thank you very much. Bye.